Just about completely filtered in. I'm Scott Robinson. I'm the manager of the microscopy suite in the basement, half of the imaging technology group. And the other half of the imaging technology group is the visualization laboratory on the 4th floor. And I would like to introduce briefly the new manager of the visualization laboratory. That's Travis Ross right here. And we're really happy and lucky, I think, to have him. And I'm going to read a very brief bio of him. Travis started his career with a BFA in 3D modeling and animation from the Academy of Art University in San Francisco. He's always had a knack for graphics, geometry, spatial understanding, art, and he has a bent towards technology itself. He spent about 10 years in visual effects, TV, and video game industry. So I told him we weren't going to say that he could help you fix your PlayStation. He won't do that kind of stuff. But he's spent a lot of time with the technical art of 3D scanning and modeling from 3D scans, creating super realistic character, prop, and environmental models. He also paralleled that career path with an emphasis on mechanical modeling for CAD packages, which is really nice because there's so much 3D modeling that goes on upstairs, and plus we have our 3D printer, so I'm really excited. What he's been doing is he's been using a lot of software that's parallel to what we have, and it's really nice to have somebody with that depth, and I'd like you to welcome Travis to the what we do, we usually start off the imaging and visualization forum with an image of the week, and this week's image of the week is some spider eyes that were collected using a confocal microscope and taking advantage of the autofluorescence in the tissue. So what you can see right here, this is just 4 images averaged and stuck together, and you can see that this is you can see 4 of the spiders, presumably 8 eyes, and then you can see some of the autofluorescence that also occurs in the cephalothorax. In a minute, in just a second, we'll introduce Ulises. I also want to tell you what we're going to have next week. Next week we are having a visit from Nikon, and we're going to have the senior applications manager of Nikon. So of the leading light microscopy companies, we have Zeiss, Leica, Nikon, and Olympus. And so they're going to come in and talk about new technologies. And then later in the semester, we may actually host a demo where you'll be able to see some of these technologies in action. And because we're doing that, we're also going to open it up to other companies to be able to do the same thing. So today, we're lucky again to have Ulises Cervantes-Pimentel, and he's going to talk about Mathematica for CUDA and OpenCL programming.
Okay, well, thank you. Thanks for this opportunity to present you some of the new features in Mathematica A. Mathematica A came out around November of last year. Okay, and one of the big features, I think that we are also very excited about these new features, is that we are giving tools, we are providing some tools for GPU development in both CUDA and OpenCL. So basically, the main developer is Abdul, Dakkak, who is here also, and he's going to be presenting part of the material at the end of the presentation. So basically, Mathematica A provides a large number of new features that allows us to very easily and in a very integrated way develop tools to combine libraries, external libraries, and compile programs, and basically with all the features that Mathematica offers with the symbolic processing, this gives us a very powerful tool to develop these things. So this is just some images generated with the version A some of the features. This is generated with CUDA. Okay, and then we have other statistics and free-form linguistics, and there are a lot of new features. But something that we want to emphasize, especially for people like you that are the developers, is that, well, you are scientists, so basically you are going to make use of these new tools in a very productive way. Basically, there are 4 components that are new in version 8. One is called library link, Symbolic C, compile, and the C compiler driver. Library link basically is a replacement for what most people are used to use when they use Mathematica, which used to be MathLink. MathLink was the interface that allowed you to write communication programs between your own code and Mathematica. Basically, it was a TCP IP-based interface. Okay, that's the normal way that people used to write their interfaces to Mathematica. Okay, so with version 8, there is a new component that is called library link, and what it allows you is it allows you to access your external libraries directly into Mathematica. Okay, so you don't really have to recompile them using MathLink, or you don't have to write a special interface for them. So compared to MathLink, library link has the following advantages. Okay, so one of the things is that with library link, basically you share the same space of memory as your applications. So that allows you to basically avoid having to transfer data through TCP/IP to the external process. Okay, so and it also the communication it provides a very thin layer over the library function. So basically there is no loss in performance between your library and connecting it to Mathematica. Some of the disadvantages are that the MathLink, basically you were running an external process, and if that external process was buggy and it crashed, okay, it will not bring down your Mathematica session. Okay, with library link, since you are basically running this new process in the same shared memory, if something goes wrong with your library, okay, that's going to crash the whole Mathematica session. Okay, so that's one of the disadvantages. Another possible trade-off is that basically with MathLink, we have something like a parser that basically you only have to write a very minimal amount of C code to make the communication with Mathematica. Using library link, you are going to have to write specialized code just to transfer data from the internal representation of data in Mathematica to your library link. So it involves a little more of tweaking just to pass the correct arguments, the correct values. Yeah, so for example, we have a library, it's a precompiled library here, okay, that contains a function that is called demo, II, and basically what it does is just adds 1 to a number. This is a very simple example, but this is a library that is precompiled. Okay, and basically what I'm doing is that I am creating a symbol that is linked to one of the functions in that library, and I can immediately use it in Mathematica. Symbolic C, basically Symbolic C is an interface that allows me to programmatically generate C code. Okay, so basically using all the symbolic processing that Mathematica offers, you can programmatically create C programs. Okay, so basically this is the general structure for this, and then you can, in this way, you can create programs in an automatic way. Compiling has been around since version 2 of Mathematica. Compile is an option that basically tells the Mathematica code to create like a precompiled version in an internal Wolfram virtual machine. Okay, so basically what it does is that it parses the function that you want to evaluate, okay, and it creates some code that is that is run very fast. Okay, now in version A, basically what you can say is, okay, I want to compile this function, but I want to generate a C file, a C function.
It's been a long time since I've done C stuff. Symbolic C, I don't even know if it's new or not, but that's. Is there any things like mapping or scatter gather, any functions like that? Is that optimized for CUDA, or are you going to get to that stuff?
We're going to get to that stuff. Okay. Yes, it's in a moment.
Symbolic C is a way to write the C, abstract syntax tree and then convert it to
Yeah.
a source.
Mhm. Right.
It's not going to generate anything from mathematical function.
No, no.
It's a way to write C.
Right.
Not nice.
Okay.
And finally, the last component, okay, I have a way of linking Mathematica to a library, or to library functions. I have a way of generating C code. Okay, I have an automatic way of generating executables using that C code, but I can also compile C files. For example, this command C compilers tells me which compilers are installed on my system. In this case, I have 2005, 2008, and I have the MVCC compiler. Okay, so Mathematica will be able to use either of those three compilers to generate programs and to compile them. Mm-hmm. So in this case, basically what I'm doing, okay, I'm taking a MathLink program, okay? If you already have some MathLink programs that you have developed over the years, you can compile those directly into the system. So this is very convenient because you only have one system. You don't have to start switching between your prototyping notebook. Okay, you are working on a problem. You are prototyping the problem, and you don't have to keep switching back and forward between the Visual Studio IDE or your command window for GCC and so on. By the way, on Linux systems here, you are going to have the GCC compiler. And the same thing on OS 10. You're going to have the compiler native to the system that you are running this on. Well, just very quickly some of the other Mathematica features that are not exactly related with CUDA, but basically that makes working with data very, very simple. Probably a lot of you have heard about Wolfram Alpha. Okay. Okay, so how many people have heard about Wolfram Alpha? Okay, I think that now we go to the conferences and most people know about Wolfram Alpha and they don't know about Mathematica. Okay, so that's kind of sad because Wolfram Alpha is built with Mathematica, but nobody knows that we are using Mathematica for that. So with Mathematica, basically from inside your notebooks, you can call directly to, oops, I don't have a network here. Okay, well, if I had a network, I could run this directly. Okay, and basically what it will do, it will connect to the Wolfram Alpha server, and it will get data. It will do the interpretation of this command. Okay, and it will give me which is the Mathematica representation for it. Okay, so I have the presentation on a USB drive. So if you are interested in trying this later on, okay, just talk to me after it, and you can get a copy of it. Okay. So for image processing, version 8 provides a very large number of new functions, built-in functions, okay, for image processing. I think that somebody at the company already came to give a talk about all the image processing functionality. We have a whole wavelet transforms, and there are a very large number of statistics distributions and a lot of import-export formats and so on. So there are a lot of new features that make it very convenient for Mathematica to access and process your data.
Hey Ulises, can we interrupt for a second? Would it be helpful if we went ahead and got a connection for you?
That's the only example.
I think that was the only example that
just
used
wanted to check.
Okay, thank you.
Well, actually, yeah, because we're going to share the website.
We can get a connection for you in about 25 seconds. Probably.
Okay, great. So if you can do that. Meanwhile, I will keep talking about this.
Well, 25, we'll see.
Well, while he's doing that, I do have a question.
Sure.
When you were talking programming in C, are we talking straight C or C++? Is it able to accept C++ programming?
Yes.
Okay, so some of the commands that we use in C++ will be able to import directly the Mathematica.
Right. If you have a library that you already compiled, it doesn't matter where it came from, C, C++, Java, or whatever.
Okay.
You can, with the library link, you can access those functions directly in Mathematica.
Okay, now you had mentioned one of the disadvantages of the library link was the fact that you still have to write code in both Mathematica and in your C program. Are you guys working to fix that so you can just write it in one instead of having to write it in two?
So when we say you have to write in both Mathematica and C, we just say you have to write this library function in Mathematica. And in the C part, you just have to write some very, very like 3-line wrapper code.
Right, but if MATLink did it for you before, why not have
So
library link?
yeah, we're thinking of that, but we don't have
Okay.
that.
So let's see if, okay, this works. I should have tested this before. Okay, so here it is. So basically this output came directly from Wolfram Alpha, and it's telling me, okay, if you want to solve a problem that the freeform, the way that regular people write it is, okay, I want to blur this image with a radius of 20. This is the Mathematica command that you will use. Okay, and if you want the whole Wolfram Alpha output, okay, if you go to the website Wolfram Alpha, okay, this is the output that you will get if you type in this command. And from here, basically, you have okay, how you write this in Mathematica, okay, and some examples. So the learning curve, this is going to make it a lot easier because you don't really have to go through the whole documentation and learn all the list of commands. You basically, the idea is that you can kind of try to type in what you want to do, okay, and this linguistics engine basically is going to try to represent that in a programmatic way. So what is CUDA link and OpenCL link? These are two things that CUDA link is. It's a way for Mathematica users to access the graphical interface, your video card, okay, and integrate that access, okay, in a very sensible way with your workflow. So you don't have to think too much about, okay, now I need to compile this using CUDA or OpenCL, whatever I have on my computer. So you just go and start prototyping your code. Okay, and basically with these two packages, CUDA link and OpenCL link, you can access those functions and make them as native Mathematica functions. What this is not, basically we are not trying to make all the Mathematica functions GPU aware. Okay, one of the questions that we have been getting very often when we present this at conferences is that people think that all Mathematica functions are now CUDA accelerated or OpenCL accelerated. Okay, we are definitely not going there. Just some functions like an integrate or an integrate, they have taken like 20 years of development, okay, to get them to the point where they are now. Okay, imagine how long it will take us to port all that code into CUDA on OpenCL. So at least for now, we are not trying to replace the Mathematica functions with GPU versions of all of them. And that means that if you have a Mathematica program, don't expect that automatically will rewrite the whole thing and speed it up using the GPU. Of course, we would like to have that, but not yet. And the compile command in Mathematica, currently it doesn't generate CUDA code, but that's something that we are exploring, basically. Okay, that you can give any program in Mathematica, and we are trying to come out with a consistent way of generating CUDA or OpenCL programs directly for you. So once that you, if you have a workstation or a laptop that has either a CUDA capable, that means an NVIDIA GPU, or if okay, or even an AMD video card, basically with you will be able to run OpenCL on an AMD card. So this command CUDA-Q, what it tells you is, okay, if your system supports CUDA, okay, and we have something similar for OpenCL. So yeah, this system supports both. Okay, when you wanna get if you wanna get the CUDA, okay, what kind of GPU I have in this system? Okay, so you can get the information directly there. Okay, you can have the same thing with OpenCL. So basically, you can get all the information that of the hardware that you have. If I had a system with more than one GPU, this is going to give you basically a list with all the different devices that you have access to. Okay, and all this information can be also be found using the system information of the, that is the global system information in Mathematica. So here you will see, can you see that? Probably not. Okay, yeah. So we go here to links, and then we have an entry that is CUDA, that basically tells me all the information that I need to know, the device driver, library versions, and the GPU that I have in the system, total memory, and the same thing for the OpenCL. Okay, so this is a very simple way for you to very quickly detect which kind of GPU you have in your system. Some of the built-in functions that we try to provide were something that basically gives some of the basic image processing versions. So these are very simple operations, okay, but they are basically run using CUDA. And all the code, all the CUDA functions or OpenCL functions, we are providing the source code for all of them. Okay, so basically for all of these functions you can access how they were implemented. So that will give you a very quick way of starting working on your own programs. So CUDA dot basically is an interface for BLAS. With CUDA dot, basically we detect if you are given a matrix or a vector, okay, and what you want to do with them, you want to multiply them, okay. So we will call the corresponding BLAS function, the corresponding CUDA BLAS version. Also the same for the CUDA Fourier. Okay, so for people that are familiar with the CUDA toolkit, basically they provide these BLAS libraries and the fast Fourier libraries. So these are Mathematica interfaces to those libraries. So just a very quick example of how you program CUDA in Mathematica. For now, basically you have to give what is called the CUDA kernel, your source code. Okay, this is plain CUDA basically. You see papers or you see on websites that they implement a new CUDA program, a new CUDA function, and they only give you basically this part. Okay, they don't tell you, okay, that you need to install the CUDA toolkit, you need to configure your environment variables, and you need to write how to pass the memory, how to synchronize. All that process, basically, you don't have to worry about any of that. Basically, you can just get the code that you want to run in CUDA or OpenCL, okay, and Mathematica will do all the necessary steps to generate, in this case, is creating an object that is a CUDA function, okay, that is basically a link to a compiled program in CUDA. Okay, it takes, well, we will see what the arguments are, okay, but basically, I generate a list of 64 integers in this case. Okay, and then I run the CUDA function that I created here. I run that on that list, and this is the output. So this is a very, very simple example. So basically, what's the interface that we have to compile your own CUDA programs? In the CUDA program, CUDA kernel, basically you have the definition of your function. Okay, basically you have the name of the function and the arguments. Okay, the CUDA function load how you are going to interface to that function is by specifying the source code, specifying which function you want to compile, and basically you do this mapping between the arguments into something that Mathematica understands. So basically, pointers to integers or pointers to floats or so on, you have to give them inside a list. In this case, it's a list of integers. And arguments, okay, in this case, they are just without the list brackets in this case. So that's basically the mapping that you need to do between your CUDA function, between your CUDA program and the way that Mathematica loads those. So what does CUDA function load do internally? It does all these 7 steps. Basically, it checks the arguments that they are correct. It involves the MVCC compiler to compile your C code. Okay, all the inputs that you declare as inputs, okay, basically they are going to be loaded to the GPU using a function called CUDA memory load. Okay, they are going to send they are going to send all this for the GPU for computation. It's going to wait until the computation ends, and then it's going to get back all the data back into Mathematica. Okay, so all of these steps are being done automatically by just this function, CUDA function load. So you don't have to worry about any of these steps. So something that has come out very recently is that now GPU with double precision are more available, and they are more they are cheaper now. Okay, you can buy a very good GPU card for how much? $50 or, well, no, the $500 is the double precision, and the single precision is $50. You can buy a video card for that. Okay, but then how do you do that? How do you write a program that is aware if you are in single or double precision? So we introduced a new type that is called real_t. That basically these functions, CUDA function load, they are going to detect what's the precision of your GPU. If you are running on a single precision GPU, it's going to replace this real t by a float. If it's a double precision GPU, it's going to replace this real t by a double. Okay, so that way you can write on your code only once, and you know that that program is going to run at the highest precision based on which system you are running in. And Mathematica doesn't support these many types, but CUDA and OpenCL, they support a much wider number of types. So basically all these types are being supported. Okay. So one of the things is that with CUDA, you can create, with CUDA Link you can create your programs, you can compile them, okay? But they don't only have to live in the, as a Mathematica function. You can create executables, you can create object files, cubing files, PTX files. Okay, basically you can prototype your whole CUDA or OpenCL programs in Mathematica, and then you can use that code somewhere else on your own systems. So we have some symbolic way of generating CUDA code. Okay, basically this is it's very similar to Symbolic C. It's an extension of Symbolic C, basically. But what it does is that it can generate CUDA and OpenCL functions. So very quickly here, started with OpenCL link. It's going to be exactly the same interface. Basically, if you want to use OpenCL instead of CUDA, you don't have to learn anything else new. It's going to be basically the same interface. You only change, instead of CUDA, you put OpenCL for the function load. In this case, this is a very simple example. Well, not very simple example. It's an example of a ray trace fractal, okay, that is written in OpenCL, okay, and it's a ray trace version of that. Okay, so yeah, so if you're familiar with both CUDA and OpenCL, this is just something that you just need to translate between an OpenCL and a CUDA program. Okay, so these are the keywords that you use in CUDA, and these are the corresponding keywords that you have to use in OpenCL. Yeah, and the syntax is the same. You give in this case it's an OpenCL program. Okay, instead of using CUDA function load, you use OpenCL function load, but the rest is exactly the same. Okay, so and then you just run your OpenCL program. So the new MacBook Pros now, they are coming with an AMD processor instead of an NVIDIA processor, which means that on the new Macs you will be able to run OpenCL, but you will not be able to run CUDA. Okay, so having this feature that you can either run it with Mathematica, you can develop for both CUDA or OpenCL, that really allows you to use your Macs for GPU development without any problem. Yeah, so this is basically what I just been saying here. So this is a schematic. Basically, if you don't use OpenCL, you use the traditional way of compiling CUDA or OpenCL programs, you have to take care of all these steps. Okay, allocate memory, all the memory management, transfer, synchronize threads, and do all of these steps. basically what we are doing here is that we are putting a layer before and after you actually execute. So with CUDA Link, you only have to worry about implementing your CUDA kernel code or OpenCL code, and all these steps are taken care automatically. So for the workflow, this is very convenient because basically you start prototyping. You on the same place you are running your programs, compiling, okay, all behind the scenes, and you test, and then you can go back and keep working. So it really simplifies the workflow. In this case, this is okay. Let me do something here. I think I have many things running before. So here I have a program, okay, and I want to prototype it. So I want to do some image processing, video processing, so I can change the program. And it automatically did everything. Because I have something that in Mathematica we use that is dynamic, okay, of the source code, which basically is telling me that any time that you change this source code, it's going to reevaluate this code. Okay, so in this case, when I change the source code here from that value to this value, okay, let me. Okay, so basically here I can just start playing with some of the parameters. Yeah, and it automatically compiles a new CUDA program, okay, and it runs it. So this makes very, very convenient to do development in place. So for now, I'm going to switch so Abdul can present you some more examples. Are there any questions at this point in the meantime, Abdul? Yes?
I missed this call. Is there a way to talk about the different CUDA cores you might have on the computer? Do you have 2 or 3? Some laptops at least have 2. Can you tell Mathematica to send it to one or the other?
Yeah.
Yeah.
He's going to...
So automatically, is this good? Let's see. What is this?
This is the microphone, and this is another microphone. You have 2.
Oh, okay.
Okay. You have
Sorry.
to put that on. Yes, actually he's going to be presenting in a moment an example of multi-GPU. So, yeah.
So the ability to like rapidly prototype CUDA kernels in Mathematica is really sweet. But there's a lot of optimization, song and dance that kind of comes into play, selecting, blocking grid positions, determining what type of memory access you're doing. I'm assuming Mathematica doesn't automatically optimize for that stuff, right?
It does some of the memory transfers. Basically, Mathematica tries to do a lazy memory copy, basically.
Right.
So if you don't, it doesn't always moves memory to the GPU and brings it back all the time. Right. You can create a block of memory in the GPU and leave it there. Okay, run several kernels, and once you are done, then it will bring back the
Right, but I mean the actual kernel execution.
Right, so most of the interesting optimization that you could do is in the kernel, right? So, and you can change whatever you want. So in this case, this is as optimal as you can get.
Well, but I mean, like,
But
let's say you're blurring a 2D image, it's probably
Right.
going to be advantageous for you to use, say, cached texture memory in that case.
Right, so we don't have support for textures,
Yeah.
but you can use shared memory and all these things. But usually the optimization is in this part, and you have access to the entire thing.
Yeah. Yeah, no, that absolutely.
Right, and this is maybe, you can, I don't know of any system where you can kind of just be playing, develop like 10 filters in 2 seconds. Not 2 seconds, 2 minutes. As fast as you can type, and compilation usually takes half a second, so. So one thing in CUDA, why you would use CUDA is the mic good?
It sounds
Okay.
good to me.
Okay. One reason why you use CUDA link and OpenCL link is because the Mathematica language is rich. So it's a functional language. It pattern matching languages. You know, if you're a computer science, it's kind of very, very interesting language. So you can do, you know, application, and then this is the map operator. You might have heard of it. You know, like everybody's now learning about Haskell and Scala and all these things, but 25 years ago, we had them called maps. You know, it can find like all the tuples or all the permutations of a given list. The list can be images, and you know, give it as a graphic. You have access to the visualization functions, which you know you don't have to write your own your visualization. A lot of times, you know, your CUDA kernel is, you know, maybe 100 lines long, but the stuff that has to be around that is, you know, thousands of lines long. Typesetting, another, you know, thing. You just say matrix form, and it gives you a typeset that you can export to TeX or you know, EPS or whatever you want. Another, you know, animations using dynamics and animate. So in here, I'm doing an image convolve and varying the size of the Gaussian matrix from 0 to 20 with increments of 1. So you know, and it's not reserved to the built-in functions. You can do a CUDA function load, and then you know apply it to an image. But then you can say, so once you have a CUDA function load, you say, you know, here's my list of images, and then I'm going to write to manipulate. That manipulates with the images. So then I can select which image I want, and it's running the thing on CUDA. You know, another example of visualization. So, you know, you write a Mandelbrot set or a Julia set in this example. You know, it looks complicated, but this is all, you know, variable declaration. This is where you're actually doing computation, the for loop. So, you know, you do the thing where you're saying CUDA memory. You're saying, you know, allocate a chunk of memory and leave it there. Don't deallocate it. Then you load the function. Another interesting thing is you can pass in these defines. So if the compiler knows that, okay, these are that many loops, you know, I'm only considering that many loops. So, you know, you have like for I equals 0 to I equals 10. Then the compiler can unroll the thing and optimize it. But you usually can't do that in a production. You know, you can't just give something to a user that's, you know, and say, okay, but you can only do this for, to n equals to 10 or n equals to 1,000. But in this case, you could, because the user can modify it and you know, and change it. You know, you can create all variations of all CUDA functions that, you know, as the iterations change. Once you have that, you can put it inside of manipulate and visualize it. So I'm not sure, you know, how you know, you can do that with OpenGL and C and figure out how to compile the thing on Windows and Linux and all that. We also have extensive examples, you know, demos, and we provide the source code for that. This is volumetric rendering. You can put in whatever volume you want and change the transfer offset and scale, the transfer functions, all that, the colors. All, you know, this is probably like 200 lines of Mathematica, not terribly complicated. Another feature is that, you know, sometimes you don't want to be just going, porting the entire application into CUDA. You want to say, okay, this part is, either you want to do it in steps. So you have a Mathematica program, you want to make it faster, you want to either do it in steps, or you have just one core function that you just want to optimize. So you'll find this like in molecular dynamics. You just have one function that's doing 90% of the work. So in this case, I have a convex hull algorithm, and the algorithm is, you partition it. The most time-consuming part is like finding the, some part of the hull, and then you merge them together at the end. So this is my CUDA program. I load it using CUDA function load. Then I have a standard Mathematica program, and then you use CUDA sort to sort the array, do some pre-processing, and input points, and then compute the hull. So it's okay. Okay, so and then I visualize it. So these are my input points, the green ones, and the hull is the brown. So you don't have to go, from, you can do the transition in steps. Sometimes most algorithms are not fully parallelizable. So chunk of them are, a small subset of it is, and that you can use CUDA for that. And one thing is, it's scalable to multiple GPUs. So we have something like Grid Mathematica and parallel tools where you can use all the GPUs on the system. This system only has one GPU, but I can still kind of cheat. So I'm going to launch 4 worker kernels. I'm going to say, you have to do needs CUDA link to actually use CUDA link. So I'm going to do parallel needs, which says, for all worker kernels, do import CUDA link, essentially. Evaluate this statement on all GPUs. So usually you'd have, if you have 6 GPUs, then you would say just kernel ID. In this case, I only have 1 GPU, so I'm going to just say all worker kernels are just going to use the same GPU and let the thing figure it out. Then going to define my Mandelbrot kernel, say distribute definition. So this is going to share the variable with all worker kernels. Do a parallel evaluate. So this is going to load the function on all worker kernels. So you have 4 CUDA functions, and do a parallel evaluate. And that you get each one of these Mandelbrot sets was computed in a different kernel. If I had 4 GPUs, then it would be computed on 4 GPUs. And I can also plug this into lightweight Wolfram Grid Mathematica, which means I can register remote kernels and say, distribute, do this evaluation on this cluster of machines. There might be 2,000 GPUs if you have.
Can you just like strike this across them, or like load balancing, or?
Yeah, so all the load balancing is done for you. You can specify there's options to this, how to do the scheduling and all that. So everything is done for you.
Cool.
You can, if you want, you can manage it yourself. I wouldn't want to do that.
That's great.
But, so recommended next steps. So one thing is what's new in Mathematica. So Mathematica is not just about CUDA. That's what we're here to talk about. But you have the free-form linguistic inputs. So where you say something like you say equal integrate sine of x. Oh, okay, just integrate sine of x, and then it figures out what the command is. It's very good for if you're still in calculus. You know, you don't have to learn the command. That's the idea. Probably the other important, you know, thing is image processing and wavelet analysis. So in image processing, we have more segmentation, you know, health transforms and all the deblurring, denoising, and all the stuff like that. Probably, you know, in software development, you have the Symbolic C part. The CUDA and OpenCL support has a few examples, you know, how to how to use, there's a function called fluid dynamics that, you know, you just type in needs CUDA link, CUDA fluid dynamics, and you get a fluid dynamic simulation. Is it moving?
It was moving fast.
Let's try it again. Okay. So you can evaluate this in Mathematica. It's not a good internet connection. So the other resource that you're probably interested is the CUDA white paper, which if you go to Wolfram.com and then just scroll down to simplifying CUDA programming and then say download white paper, and it's also in the back. There's a few copies. I don't know if there's any left.
If you don't want to fill in the form, you can just pick one.
Right. Check the CUDA link and OpenCL link documentation pages. So those are also on the web. So any function, so let's say CUDA function load, we talked about that a little bit. You know, you have a few examples, well, a lot of examples. So, you know, all the applications and generating Perlin noise, for example, computing histograms, doing color conversion. Same thing for OpenCL. You know, there's a tutorial pages and guide pages. So in the application section, you might be interested. So the convex hull is in there. Random number generators, which there's a lot of literature about, and you know, parallel random number generators and quasi-random number generators. There's many examples on that. There's an example on generating symbolic C, you know, going, you know, from a Mathematica sort of syntax to CUDA syntax using symbolic C. That's also in the application section. And you know, all the reference pages have extensive examples. So I think maybe, yeah. So I had something about finance, but I'm not going to show it. Maybe in the end we can show it. But so if you have more information, you know, you can download a trial. You can schedule a technical demo. Contact us. I mean, I guess we're right across the street, but don't knock on the door and try to get in. Internships. So we're looking for motivated people who are can develop more examples for CUDA and OpenCL or work on different topics. So if you're interested, you know, send an email to Ulises or me. These are our emails, and submit a form.
Yeah, the internships are open the whole year, so you don't have to wait for the summer. Okay, so at any time during the year, you are
right, and
welcome to apply.
Yeah, and there's like a career pamphlet, and the Ulises card is back there also. Oops. So questions? Yeah.
What is the guarantee Mathematica provides for the output of the program? One thing I care about is because the program gonna execute on heterogeneous platforms, multiple GPUs and CPUs. So maybe each of those floating point units on those processors have different precision accuracy requirements. And because I'm using non-visual program, I care about the accuracy of the computed output.
Right.
But what is the guarantee you provide, and how do you?
So you're writing the kernel, though. So you have to provide the guarantee. We can't provide that for you.
Well,
and also, the other thing is, if we provide a guarantee, that means we have to double check against a slow version, a exact symbolic program, which kills any performance you would gain. So the one thing you can do is write the program using Mathematica, symbolic syntax, which, that's, I don't know if we can say guaranteed, but no software is guaranteed to work, but it has been, that has been used for 25 years without major issues. So, write that in symbolic form that uses exact, and then cross-check it against whatever GPU kernel you're writing.
So can you control the scheduling of your thread on each of these individual GPU cores? Can you control the scheduling?
No, because that's not provided by any API. And the CUDA doesn't, you can only say I'm launching this function on the GPU, and it's going to wait until that function finishes execution. If you're only using half of the GPU for computation, then the other half is not being used. It's just a little cycle. So most of these examples, I'm not using the entire GPU, so I'm kind of just wasting resources essentially. So that's what the optimization is, to use the full GPU. But yeah, then that kind of depends on the block size, how you're accessing memory and stuff like that. So the block size and grid size, you can modify. You have to specify at least the block size. But the grid size, we can get that for you. Yeah.
Is there any specialized design for debugging the CUDA code?
Not yet. It might in the future. If you write a program that has syntax errors. So let me go here and just put like a bunch of X's or something. Then when you do the CUDA function load, it's going to tell you compilation failed. And then it tells you, put this option in. So I'm just going to copy it and paste it. And then you can see what the output, identifier XXX is not defined. So this is the compiler telling you that, okay, CUDA NOP compile the thing. But yeah, we're thinking about adding profiling and profiling tools, debugging tools, the ability to take CUDA function and export it to C.
Now that you're going to be saying, I'd like to speed up the slowest line of my Mathematica code semi-easily, it'd be great to see that once highlighted.
Right. So you can do that. For just regular Mathematica, not using CUDA, so Mathematica has Mathematica Workbench, which is an IDE for developing Mathematica, and that has a profiler. So you just say profile, and then your whatever command, and it tells you, that many seconds was being spent on this line, and these many calls were done, and then you can click on it and it jumps to that source code.
So if there are many questions, please feel free to send us. If you are interested, or if you know somebody that might be interested in being an intern at Wolfram, we are more than welcome to hear from you.
We should say thank you while there's still appreciate you guys. Thank you also for I'm sorry I didn't introduce you too.
How do we turn this off?
I came in a couple minutes late, so I missed out. What kind of speedups have you seen, in your best cases?
Well, it depends on the application. For some of the financial universities,
Yeah.
100. So, yeah, of course, it depends on the problem and the size of the problem. Okay, you have to go to really see the scale. For other ones, for some of the image processing stuff, for example, small images, it will stay the same, C or CUDA, because there is
The implementation that you have, all the CUDA XXX names that you have, are going to be at like 80% of what you prefer.
Yeah,
Yeah.
as in any other program, the bottleneck right now is CUDA. So, everything, all the speed up that you gain running on the GPU, you lose it.
Thanks. Okay, well, thanks all. Okay. Sure. All your slide, everything on your slides is available kind of on the documentation?
Yeah, everything in the slides is in the document. We're also having like webinars.
Yeah, I forgot to ask you
This is
before
based
we
on
started
the
about
webinar.
internet. Yeah, I'm sorry.
In 2 weeks.